Hello everyone. So as you have already seen a video of a CDP sheet on my channel. So in this video we will see how to calculate the data for CDP. So four things we need to put in ABAQUS for CDP. That is first yield stress, inelastic strength, and again in damage parameter, inelastic strength, damage parameter, and for tension we have cracking strength, which is similar to inelastic strength. So first I am using simplified damage plasticity model for concrete by Milad Hafizul Grami sir, and here he studied many models, he reviewed many models, and from them here you can see a new model is developed. So first of all, let me clear all this thing. First of all, we need some formulas here. The formula for inelastic strength here, inelastic strength. It is formula for inelastic strength, and this formula is for yield stress. So first formula is this one, second this formula, and third formula which we will use is for a damage parameter. Here damage parameter in compression, this is third formula, and fourth formula damage parameter in tension. Now in this paper they also give some data for B20 concrete, B30, B40 and B50 concrete. Uh, Here B40 concrete, B50 concrete and so on. So first understand the terms which was in formula. So let's write the formula. First formula we need most is sigma c equals to sigma cu to epsilon c by epsilon dash c minus epsilon c by epsilon dash c square. Now let's understand the terms in this. First, sigma c, that is yield stress, and epsilon c is corresponding strength. Sigma cu is ultimate strength, which is cylinder strength. We get this strength from our lab data. So ultimate strength of concrete, and here epsilon dash c is ultimate strength. This strength was given in this paper. Here you can see sigma cu and epsilon c were nominal compressive stress and strain respectively, and sigma cu were ultimate compressive strength and the strain of unconfined cylinder specimen. Okay, now E dash c equal to 0.002 as per the park, and this value was also assumed in this study. So we got this the value. Now again back to formula. here. So in this formula, we get sigma Cu, which was our lab strength, and E dash C, that is 0.002. So here E dash C is to 0.002, and now sigma Cu. We need to calculate sigma C. So first we need to create a table, and in that table, what we want, let me show you. First we need yield stress, and then second total strain, third inelastic strain, fourth I think damage parameter. Mhm. Okay, so yield stress is sigma C, total strain is EC, inelastic strain is EC inelastic, damage parameter is DT. Now the value of sigma C, we need to define the sigma C. For example, our peak strength, uh, let's say 25. 25 is our FCU, 25 MPa. So sigma C, we need to increase the value. So initial value of sigma C, let's take 8. I will show you why I am taking 8. First, let's take 8, then 10.2, then 12.8, then 16, 15, 16.8, then 18.2, 18.2, then 19.2, again 22.2, now here 25. Now reduce this value again. We have 22.2 and so on up to, similarly reduce these values like 22.2, 19.2 and so on. Here 18.2, 16.8 and so on up to 10.2. We get here 8, no 10.2, it's 8. 8 and give one more value, that is like 3 or 4. 10. So we need to define the sigma C values. Now in this formula, what we have, we also get sigma C. We have sigma CU. We have epsilon dash C, that is 0.002. Now we can calculate the epsilon C, that is total strain can be calculated. For this, we need to derive this formula, and I will show you how. We have the formula that sigma C, sigma CU to epsilon C by epsilon dash C minus epsilon C by epsilon dash C square. Okay, now it will become sigma C by sigma Cu, that is equal to 2 epsilon C by 0.002 minus epsilon C by 0.002 whole square. On solving this, we get sigma C by sigma Cu equals to 1000 epsilon C minus 251,234 epsilon C square. So we get will become a quadratic equation. So 251,234 epsilon C square minus 1000 epsilon C plus sigma C by sigma Cu equals to 0. So it is in the form like ax square plus bx minus c equals to 0. Our value of a will be 2, 5 and 4 times 0. B will be minus 1000 and C will be sigma C by sigma CU. Now if we solve for x from equation that is x equals to plus minus okay, now that x equals to minus b plus minus under the root b square minus 4ac by 2a. Here, now from this we get two value of x, that is x1 and x2. x1 will be minus b plus under the root b square minus 4ac by 2a, and similarly x2 will be minus b minus under the root b square minus 4ac by 2a. Okay, so we will get this value x1 and x2. Now among this value will be greater, x1 value will be greater. This value will be greater. So we can say that x1 is greater than x2. Now let's understand from graph. Here we have the graph. Let me zoom this graph. Okay, I told you to initial value. So initial value we have to take such that it lies under this elastic region. Here up to this limit it is elastic region, and we can say that this region, under this region somewhere sigma c will lie. A sigma c which will be less than 0.5 times of sigma cu. We can say that in this region we can say that a sigma c will lie which will be lesser than 0.5 times of sigma cu in this region somewhere. So 8 is less than 0.5 into 25. Okay, so at that uh, at uh, strength of sigma c equals to 8, for taking sigma c equals to 8, we get some strength from the formula we derive, strength of any value x1 or x2. So if we use this strain and stress value, we can find elasticity, that is stress upon strain, because it is linear. Up to this point sigma c naught our value will be linear, and sigma cu will lie in this region which is an elastic region. So from this point we can find our elasticity Young modulus, that is E naught, the initial Young modulus. Now let me take you here. Okay, here we have sigma cu and corresponding strength is 0.002. For every value of stress up to this, we get two values of strength. For example, here I have take sigma cu. Here, here I get one and two value. Okay, from this for particular sigma c, I get two value. That is positive root and negative root. It means that can be x1 or x2. And if we have already seen that uh, x2 is lesser than x1, or we can say that x1 is greater than x2. So this value will be x2 and this value will be x1. So here our 0.002 is strength and sigma cu up to this value, from here to here the values will be x2, and after that the values will be x1. So now let's back to our table. Here we got two more values, x1 and x2. X1 and x2. We get two values, x2. Now from this point to this point, we have to use x1 value. This will be our x2 value, and after that point we have to use our x1. Up to this point we have our x1 value, and after that we have to use our x2 value. Again, understand the graph. Uh, okay, we have graph like this, and here we have our sigma cu, that is 25 ampere, and here somewhere in between we have our fcu equals to 8, and here we have like 10.2 and so on. So for all these values we get two value of strain, first value this one and second value this one. So here we need smaller strain, so smaller strain will what, x2. Up to this point our smaller strain will be used, our strain will be smaller, here x2, and from after that we have x1. So similarly up to our fcu we use a smaller value of strain, that is negative root, and after that we use bigger value of strain, that is positive root. Now we have to calculate the inelastic strain. So formula for inelastic strain is epsilon c minus sigma c by E naught. So first we define sigma c value, and from this sigma c we define the sigma c value. We define sigma c value. We define sigma c, and from this sigma c we calculate the corresponding epsilon c, and from first value, from first value of sigma c and EC we can find E naught, because E naught is Young's modulus and it is stress upon strain. So we can find E naught. Now for every value of sigma c and AC we can find inelastic strain using this, and also E naught will remain constant. If we have to use E naught, which is initial Young modulus, initial. So we have to use this one only. Not have to calculate for every stress or strain. We just need to calculate this first E naught, that is initial E naught, and used in all formulas. So we define yield stress, we calculate total strain from yield stress, and we calculate inelastic strain using yield stress and total strain. Now it's time to define damage parameter. So formula for damage parameter DC, we can say that it is 1 minus sigma c by sigma cu. 1 minus sigma c by sigma cu, and for every sigma c value we get DC value, and sigma cu is our ultimate strength. But in this case I will draw the graph again, no problem. So we are talking about DC. We are talking about DC, I think. So let's me write D. Okay, DC. Our concrete will damage after it reach its ultimate strength, or we can say our concrete will fail after it reach our ultimate strength, uh, and ultimate strength. So up to the value of 25, up to value of 25, our damage parameter will be 0. We don't need to calculate, and after that, from here to here, we need to calculate our damage parameter. And please note that damage parameter will always less than 1 or maybe equal to 1, but if you are getting the value greater than 1, then there is a mistake in the calculations. So every value of sigma c, we can find epsilon c, and from both these values sigma c and epsilon c, we will find inelastic strain, and from sigma c and sigma cu, we can find dc, that is damage and compression. Now let's talk about tension damage. For tension damage, we have to we need to create table similar to this. First we have yield stress, second we have total strain, third we have cracking strain. Cracking strain is similar to our inelastic strain. And fourth we have damage parameter. So now for tensile behavior, I will prefer using the evaluation of tension stiffening effect on the crack width calculation of flexural RC members. You can see by side M alarm. Okay, so we have seen uh, first we need to find our first value of yield stress. So first value of yield stress as per IS 456 2000, the first value will be 0.7 root FCK. Here 0.7 root FCK, and here FCK is just our FCU, so it will be 3.5. And if we create table, so we have yield stress, total strain, cracking strain, and damage D in tension. So from this paper they also developed a tension softening curve. You can see first tension softening curve suggested by some Mosi and second modified tension softening curve. In this we have more described regions. For example, our first FCT max, this value, this is FT naught, which is 0.7 under the root FCU as per IS code. Now second value will be 2 by 3 times, third value will be 3 by 8 times, fourth value will be 1 by 6 times, and corresponding strain is first 3 times of first cracking strain, and second will be 5.875 of cracking strain, and here 10.5 times, and here 16 it crack. In this means the concrete is totally cracked and failed. Now first value of sigma T naught, we can say we have calculated as 3.5. Second value, sigma T1 will be our 2 by 3 times of sigma T naught. Sigma T2 will be our 3 by 8 times of sigma T naught, and last sigma T3 will be our sigma T naught by 6. Now corresponding total strength we needed. So first total strength, sigma T naught. You can see up to sigma T naught here in the graph. Sigma T naught, the value is elastic, so we can use first strength Et naught, that can be our sigma T naught or sigma FCT max. You can also say the sigma T naught as FCT max divided by our initial modulus of elasticity, because up to this point the curve is linear. So we can find this. First strength will be sigma T naught by E. Now for second one and third and fourth one, we have to find ECR first, that is this one, ECR. So for ECR we have formula like ECR ET minus sigma T by E naught. So we have sigma T, we have sigma T, we have ET, and we have E naught. So we can find the ECR value. Now for let's example, the value is ECR. Now so this value is this value will become sigma T1. For sigma T1 we need to find EC1 or ET1 we can say. So ET1 will be, let me check again, here it is ECR. You can see the value is ECR. So this value is in 3CR means 3 multiplied by this value. So here we need to calculate ECR differently, but in this paper ECR represented two total strain. As you can see from graph, it is like something like this, and here is our F or sigma T naught. Because of nomenclature I got little confused. So and this is ECR. So corresponding value here 3 ECR. This ECR is this value, and this value, this ECR is calculated as ET naught. There is some nomenclature difference in this paper. So for 2 by 3 sigma T naught we have some value of strain, that is, let me write it, 3 into ET naught, and for second value ET2 we have 5.875 ET naught, and last ET3 we have value 10.5 into ET naught. Okay, now we can calculate the value of ECR. We have formula to calculate the value of ECR. ECR is just inelastic strain. As we have calculated the inelastic strain in compression, similar formula uh, for ECR in tension. So here we can write the nomenclature is ECK equals to ET minus sigma T by E naught. For every value of sigma T we have ET. We can, for every value of sigma T we have value of ET naught, or we can say ET. We can now find ECR from using this formula, and E naught we have already got the E naught from our compression, so we have to use this one. And here this is the same value of E naught. Now we have left with damage parameter. So damage parameter in tension, the formula remains same, 1 minus, here we have sigma c, now we can use sigma t by sigma t naught. Sigma in compression we use sigma cu, but in tension our maximum strength is sigma t naught 3.5, that is. So from this you can calculate sigma dt also. Now let's move to our PC screen and see how to put this data in ABAQUS CDP model. And also I will show you my Excel data that I have prepared for this CDP.